Welcome to another discussion in ME Review. Our topic for today is about solid mensuration. Topic number 3. You can watch algebra and trigonometry in the previous discussion. At the end of this lesson, you should be able to recall the fundamental concepts and principles in solid mensuration, list important formula and equations in solid mensuration, and apply the concepts, principles, and formula equations in solving worded problems in solid mensuration. This will be the outline of my presentation. Let's first start with the polygons. There are two classifications of polygons. We have convex polygon. They are polygon with no interior angle greater than 180 degrees. Concave polygon, on the other hand, is a polygon with at least one angle greater than 180 degrees. So to understand what is an interior angle, this is how to understand what interior angle is. As you can see here in this illustration, the interior angles are the angle bounded by the sides of the polygon. The exterior angle, on the other hand, is found on the outside. So based on this, you can already differentiate what a convex and a concave polygon is. For n sides regular polygon, so when we say n sides, it can be a triangle with 3 sides because we cannot form a polygon for 2 sides only, right? So we have at least 3 sides for us to form a triangle, and then we have a square. So these are regular polygon if the sides are equal length. So they are regular polygon. So these formula here are applicable only for regular side polygon, meaning the sides are all equal. So the number of diagonal can be computed by this formula, n over 2 multiplied by n minus 3. For example, for a square, it has 4 sides. So if you substitute n is equals to 4 here, the result would be 2. So it means that square has 2 diagonal. You can also use this formula for pentagon, for hexagon, heptagon, so on and so forth. The interior angles, so the angle bounded by each side of the regular polygon, the angles can be computed using this formula, n minus 2 divided by n times 180 degrees. Say for example, for square again, so when you substitute 4, so you can find that when you substitute 4, we have 4 minus 2, so that is 2 divided by 4, so that is 1/2 multiplied by 180, so the result would be 90 degrees, meaning each of the interior angle of the square is 90 degrees each. So that's how we can make sense of this formula here. Then we have the sum of interior angle can be computed by multiplying n minus 2 times 180 degrees. So if you wanted to know the sum of all the interior angles for square, for example, when you substitute 4 minus 2, so that is 2 times 180, so we have 360 degrees. So that means the sum of the interior angle of the square is 360 degrees. For triangle, if we substitute, the result would be 180 degrees. For the exterior angle, no matter how many sides, the sum of the exterior angle would be 360 degrees. Now that we have an understanding of polygons, we are now ready to move forward to circles. For circle, we can use these key formula and theorems in order to solve problems related to circles. The area of a circle can be computed using the formula pi r squared, where r is the radius of a circle, circumference is equals to 2 pi r. So when we say circumference, it is equivalent to that of a perimeter, for example, for a polygon. Then we have for a sector, the area of a sector is 1/2 r squared multiplied by theta. Theta here should be in radians. The arc length or the length of an arc of a circle can be computed using the formula r multiplied by theta, where theta again is also in radian. For the area of a segment, that is equals to 1/2 r squared multiplied by theta, which is in radian minus sine theta. Theta is also in radian. So for us to understand the sector, the arc length, and the segment, this is how we can locate them. So we can see here the area of a sector, then we have the arc length here, and then we have the segment found here. So if you wanted to get the area of a sector and a segment, then you will use the previous formula. And if you wanted to get the length of this arc, then you have to use also the formula in the previous slide. Here are other parts of a circle. We have the chords, we have the radii, we have the point of tangency, the tangent line, perpendicular, bisector, central angle, and also we have the inscribed angle. The central angle of a circle is equal to the length of the arc. Say for example, you have here a central angle alpha, then that is equals also to the length of this arc AB here. So since your alpha is a central angle, it means that it's an angle formed by the two radius of a circle. Also, another theorem states that the inscribed angle is 1/2 of the central angle. Say for example, you have a problem wherein you are going to identify the value of the central angle, for example, given the inscribed angle, or vice versa, then you can use this theorem in order to get the value of the central angle or the inscribed angle using the relationship that this inscribed angle here is 1/2 of this central angle here. And we know that this central angle is also equals to the arc also equals to this arc AB. So if you're given, for example, the length of this arc, then you can determine the central angle, and eventually you can get the inscribed angle. So you can use any of this relationship to play around and get the unknown value. Then we have the angle subtended on the same arc are equal. Say for example, you have here an arc AB. So all of these angles that subtends this arc AB are all equal. And they are your angle beta here at point D. So this subtends AB, as you can see here. And then we have at point E, this inscribed angle here is subtending also AB. Same also with F, it also subtended, and then we also have G. So all of this, the angle G, F, E, and D are all equal because they subtend the same arc. And if you wanted to compute their value, if you have, for example, the value of a central angle or the value of this arc here, then you can also get those values. So again, this is how we can illustrate the central angle, the inscribed angle, and the intercepted arc. Another important problem is the computation of the area, for example, or the radius of a circle or a triangle that inscribed in a circle. So here, if you have a triangle inscribed in a circle, then you can use this relationship that the area of the triangle is equals to r times s. R here is the radius of the circle. S is the semi-perimeter of the triangle. For triangle circumscribed in circles, just like what you can see here, we have a triangle and it's circumscribed in a circle. The area of this triangle can be computed using the length of side A, B, and C of the triangle divided by 4 times the radius of the circle. So the radius of the circle is this radius here. So that is how you can compute also that one, depending on the unknown. So for example, you are looking for the radius of the circle where the triangle is circumscribed, then you can also use this formula. Let's move forward to parallelogram. The parallelogram can be a square. It can also be in a form of a rhombus, a rectangle, or the parallelogram that we are acquainted to, that you can see here we have two parallel sides. All of this anyway are parallelogram because two sides has parallel and they are equal, just like you can see here. So the general formula for a parallelogram, meaning it is applicable to any of these, whether it's a parallelogram, rectangle, rhombus, or square, the area can be computed using AB sine theta. So what does it mean, AB? AB is any sides that are consecutive sides. Say for example, side AB here. So they are consecutive. So for rhombus, we have here another side AB, so they are also consecutive. We also have here another AB for square. As long as they are consecutive, they are the AB. Then sine of the included angle between those two sides. So for example here, for this part we have theta here, so this is the included angle. Then you also have another one here. Then you also have another one here. So you can use this formula to get the area of the parallelogram, aside from the usual area formula that we are acquainted to from elementary days. So you can use this formula in order to get, this is a general formula anyway, whatever the angle in between, then you can use to get the area. For the perimeter, that is just equals to 2 times of the sum of A plus B, or the consecutive side. For a rectangle, using those general formula, since the theta is 90 degree, then it will reduce to 1. That's why our area is just equals to A times B. For the perimeter, it's just the same. For square, on the other hand, since the angle in between is equals to 90, so sine theta would become 1 also, and since the consecutive sides are also the same, that's why our area will reduce to A squared. For the perimeter, that is equals to 4A, since it is just the sum of all the sides. Then for rhombus, so that's also A squared, but you have to multiply it by sine theta, but because for rhombus, the theta is not necessarily a 90 degrees. Then the perimeter is also 4A, because we know that all sides of the rhombus are all they are equal. So that's why we can also use the 4A. Then we have for trapezoid. So a trapezoid is not necessarily not a parallelogram. So we have a separate formula for the area of a trapezoid, that is 1/2 the length of the base and also the head here. So we have A plus B and the perpendicular height H. So this H should be a perpendicular height, meaning it's 90 degrees with respect to the parallel side. So not with respect to the non-parallel side of the trapezoid. For the median, so this is the median here, we can also compute that using 1/2 A plus B. Let's proceed to cyclic quadrilateral. This is how a cyclic quadrilateral looks like. So it's a quadrilateral with sides that are not necessarily congruent, and it is being circumscribed by a circle. So we have here the sides A, B, C, and D for the cyclic quadrilateral. Using the Brahmagupta's formula, then you can use this to get the area of this cyclic quadrilateral. So this area here is the area of this quadrilateral, not the area of the circle, but this quadrilateral. You can use this formula where S is the semi-perimeter or 1/2 of the perimeter of this quadrilateral. For the radius of a circle, this is how we can use the area. So once you have the area here from the Brahmagupta's formula, you will substitute it here in this formula so that you can get the radius of the circle that will circumscribe that cyclic quadrilateral. A, B, C, and D represents the length of the side of this cyclic quadrilateral. Now let's proceed to ellipse. For the ellipse, this is how it looks like. So we have here a semi-minor axis, and then we have a semi-major axis. It's semi because it's just 1/2 of the major and the minor axis. So the area for ellipse is just pi AB. The perimeter, on the other hand, is 2 pi multiplied by the square root of the quotient of a squared plus b squared and 2. Now let's proceed to regular polyhedron. Regular polyhedron means that they have equal faces. So all the area of each of the face are all equal. So we have a tetrahedron, for example. So the surface area can be computed using this formula, the volume, and we can also get here the ratio of the surface area to the volume. For the cube, you also have here the surface area, the volume, and also the ratio. And for octahedron, let's proceed to regular parallelepiped. For a rectangular parallelepiped, the volume is equals to ABC. ABC represents the length, the width, and the height of this rectangular parallelepiped. The surface area is 2 times the sum of AB plus BC and AC. The lateral area is equals to 2 times BC plus AC, or the lateral surfaces. Then cube. The volume of cube is a cube. Surface area is 6a squared. The lateral area, or the area of the sides, are 4a squared. Then right prism. The volume of a right prism is equals to the area of the base times the height. So the area of the base here, for example, in this figure, we have a triangle. So you have to obtain first the area of this triangle here and multiply it with the height. So that's the volume of this right prism. The surface area is equals to the lateral area plus twice of the area of the base. So the lateral area is equals to the area of this lateral sides here. Then you add the base of the the area of the two bases. Then you have the lateral area, on the other hand, is the perimeter of the base multiplied by the lateral height. So the perimeter of the base can be computed using the formula for the perimeter, and then the length of the length is represented by this length here, which is the perpendicular height. So that's for the right prism. Then we have the right circular cylinder. For the right circular cylinder, the volume is pi r squared times height. So it's just equals to area of the base times the height. So this is the area of the base. The base of a right circular cylinder is a circle. Then we have here the height, which is perpendicular. If you're going to get the angle here, then you can get area of the base as pi r squared, since it's a circle, multiplied by the height. For the lateral area, it's the area of the lateral side. If you're going to cut this cylinder, it will be like a rectangle. So this now represents the lateral area. So the area of this lateral area is equals to the circumference, since if you're going to roll this out, this is actually equals to the circumference of this circle here. So this circle here is equals to this side here. Then that is the circumference. So that is 2 pi r. That's why we have your 2 pi r. Then the length here is actually this height also. So this length is equals to this height, and that is 2 pi rl. For the surface area, therefore, the total surface area is equals to the lateral area plus the area of the two circle here at the top and at the bottom. So that's the surface area. Then we have a right pyramid. The volume of a pyramid or right pyramid is 1/3 area of the base times height. So this is also a general formula because the base can be a square, it can be a pentagon, it can be a nonagon, whatever gon it is. So you can get that area of the base first, which is the bottom part of this, the base of this pyramid, multiplied by the perpendicular height or the height from the apex to the base, which is perpendicular. So that's how you can get the volume of a right pyramid. The lateral area is the sum of the face area. So the area of this side here, this one, and the one at the part here and here. So that is the lateral area. So whatever this lateral side is, say for example here, we have a square pyramid, then you have 4 lateral area. Say for example, these are isosceles, then you can get the area of that, then multiply it by 4. So you can get the lateral area. The surface area is the sum of these faces and also the area at the bottom, which is the area of the base. Let's proceed to the Frustum of Pyramid. The main formula that is used to calculate the volume of a Frustum pyramid is 1/3 of the height, which is the height from the top to the bottom, perpendicular, multiplied by area of the bases, which is the base at the top, base at the bottom, that's b1 and b2 plus the square root of b1 and b2. So if it is for example a square, then you have to get the area of the square here at the bases on the top at the bottom, and then you substitute it here in the formula. So that's how you can get the volume of a frustum of a pyramid. For the frustum of a cone, it is quite different. Say for example, you have, because for a cone it's obviously a circle, so we can get the volume using this derived formula here. So h is the height, which is also perpendicular to the bases. R is the radius of the lower base. R small is the radius of the upper base. The sphere. For the sphere, the volume is 4/3 of pi r cubed. For the surface area, that is 4 pi r squared. So the surface area represents the area of the surface of the sphere. Then we have spherical lune. So the spherical lune, it is actually a surface. It's not a volume. So this is a surface. So this part here, it's a surface. So to get the area of this surface, then you will use this formula here, pi r squared theta over 9d, where theta is equals to the angle here. So that is your theta, or the how it is the opening of that cut. So that is the theta. Take note that it should be in radians. So that's the spherical lune. For the spherical wedge, the wedge on the other hand, it's actually a volume. So this is actually not A, but this is V. So for the volume of a spherical wedge, that is equals to pi r cubed theta over 270. So it now represents, so this part here is the surface area of that lune. But if you include the volume here, then that's already the spherical wedge. So you can get the volume of the spherical wedge using this formula. Theta is also in radian. Let us have some example for us to appreciate how to use those formula. Take note that these examples are very limited, so you can do your own research for more examples so that you can practice this formula. We are given with a triangle of sides 10 cm and 15 cm and an included angle of 60 degrees. We are to find the area of a triangle. If you're going to examine this triangle here, so this is how it looks like. We have two sides 10 cm and 15 cm and the included angle is 60 degrees. If you're going to extend it here, it will actually become a parallelogram. So we know that the area of a parallelogram is AB sine theta, right? So that's AB sine theta, where A and B are two consecutive sides. Say for example this 10 cm here and this 15 cm, and theta is the included angle between the sides, so this is the 60 degrees. But since this is a triangle, it's just 1/2 of the parallelogram. That's why we add here 1/2. So that's the reason why in our formula the area of a triangle can be written in this way. So that is 1/2 AB sine theta. So if substituting the given value, you can get the area of a triangle. So this is another way of computing the area of a triangle, especially if it is not a right triangle or there is no perpendicular height. So it's more easier if we have the angle. Example problem number 2. In triangle BCD, BC is 25 meter, BD is 10 meter. The perimeter of the triangle may be. So for this problem, we are looking for the possible perimeter given the two sides. If you're going to recall, one way to determine if it would create a triangle is the Schwarz inequality, which states that the sum of two sides must be greater than the third side. So the two sides given here are 10 meter and 25 meter. So for this to become a triangle, our DC should be less than our sum of 10 and 25 to satisfy the Schwarz inequality. So our DC, acceptable DC is 35 and below, and less than 35, or say for example here 34, since 34 is less than 10 plus 25. So the acceptable side, the length of the third side are 34, 33, 32, all those values less than 35. So if we're going to accept 34 as a value, then the possible perimeter would be the sum of 34, 25, and 10, and that is equals to 69 meter. Sample problem number 3. The sides of a triangle are 8 cm, 10 cm, and 14 cm. Determine the radius of the inscribed circle. So we have here a circle inscribed in this triangle with given length. We are looking for the radius of this circle. So using the area of a triangle as a function of the radius of the inscribed circle, we know that that is equals to the product of the radius of the circle and the semi-perimeter. So in order for us to get the value of the radius would be equals to the area of a triangle divided by the semi-perimeter. On the other hand, we also know that the area of a triangle using the Heron's formula can be computed using this formula here, where A, B, and C are the sides of the triangle. And the semi-perimeter of the triangle is equals to the sum of the side divided by 2. So for this triangle here, the semi-perimeter is 16 cm. Therefore, we can get the area of the triangle using the Heron's formula, and it is equal to 16 multiplied by the square root of 6 cm squared. Now that we know the area of a triangle and also the semi-perimeter, then we can compute also the radius of the circle. By substituting the value, the radius of the circle is just equals to 2.45 centimeter. So the radius of this inscribed circle is 2.45 centimeter. The sides of a cyclic quadrilateral are 3 meter, 3 meter, 4 meter, and 4 meter. We are to solve for the radius of the circumscribing circle. So this is the cyclic quadrilateral. We know from the Brahmagupta's formula that the area of the cyclic quadrilateral can be computed using this formula here, wherein the semi-perimeter of the cyclic quadrilateral is the sum of all the sides divided by 2. Substituting those values, we can get the semi-perimeter as 7 meter. So we can get the area of the cyclic quadrilateral using the Brahmagupta's formula, and we got the area of the cyclic quadrilateral is 12 centimeters squared. The area of the cyclic quadrilateral is related to the radius of the circle using the formula that you can see here. And if we're going to solve for the radius, then we can substitute the value of the area and also the length of the sides of the cyclic quadrilateral for us to obtain the value of the radius of the circle, which is 2.5 centimeter. So this is how we can use the Brahmagupta's formula and the relationship between the radius of the circumscribing circle and also the sides of the cyclic quadrilateral, as well as the area of the cyclic quadrilateral. Sample problem number 5. The rhombus has diagonals 32 and 20 inches. Determine its area. So in this problem, we're given with the diagonals. So for our rhombus, we have these two diagonal here. So the first one has a diagonal 32 and the other one is 20. So if we're going to determine the area, we know that the formula for the area of the rhombus given the diagonal is equals to 1/2 d1 and d2. So 1/2 of the product of d1 and d2, because if you're going to examine it, so this is the d1 and then we have the diagonal d2. So we can actually use the diagonal to solve for the area of a rhombus, aside from the adjacent or consecutive sides. So substituting the value, we can get the area of the rhombus as 320 inches squared. Find the area of a regular octagon inscribed in a circle of radius 10 centimeter. So we have here a regular octagon. It has 8 sides. It's a polygon with 8 sides. And it's inscribed in a circle of radius 10 centimeter. So first we're going to determine the angle for each acute interior angle. For each acute angle based on the center. So this is actually a central angle. So first we know from our knowledge that each of the angle is equals to the whole 360 degrees divided by the number of sides. So if you're going to divide this octagon, it would actually have this 8 acute angle here, which is corresponding also to the central angle. So we have 45 degrees. All of these are equal. So we have this 1, 2, 3. If you're going to count all of that, that is actually equals to 8. And we know that the total of all of this, since that is a complete revolution, it's 360. So 360 divided by 8, that's what we can get each of the central angle as 45 degrees. So that's why we have here 45 degrees. Thus, the area of a one triangle can be computed already, since we know the sides. Those are 10 centimeter because it's equal to the radius. All of that are 10 cm. And also the included angle. So we know that the formula for a triangle given 2 sides and 1 included angle is 1/2 of those sides multiplied by the sine of the angle. So if we substitute the sides and also the angle, then we can get the area of a triangle. So now that we have the area of a triangle, then we can get now the area of the whole regular octagon by multiplying it by 8, since what we got here is just for one triangle, and then we have here 8 triangle, then we have to multiply 8 to the area of each triangle. So the area of this regular octagon is equals to 282.84 square centimeter. Sample problem number 7. Find the area of a regular pentagon whose side is 25 meter and the apothem is 17.2 meter. So we have here the side. This is a pentagon. So the pentagon, if you're going to look at it, this is the side here. The side is 25 meters. So each of these are equal since this is a pentagon, regular and side. Then we have the apothem. So the apothem is the distance from the center to the base, or each of this side rather, perpendicular. So that is the apothem, and this is 17.2. And if we're going to examine this pentagon, we can actually form 5 triangles. So we have 2, 3, we have 4, and then we have the last one, 5. So each of these has equal area. So what we can do is to get the area of just one triangle and multiply it by 5. So for the area of one triangle, if you're going to examine it, we have the base and the height already, and they are perpendicular. So if they are perpendicular, then we can use the regular formula. That's 1/2 base times height. So that's the area of a triangle, right, from elementary. So the area of a triangle here would be equals to the product of 25 meter and 17.2 divided by 2, so that is 215 square meter. So to get the area of this regular pentagon, we multiply it by 5. So the area is equals to 1075. This is not centimeter but meter squared. So 1075 square meter. Sample problem number 8. The angle of a sector is 30 degrees and the radius is 15 centimeter. What is the area of the sector? So this is the area of the sector bounded by these green lines and curve here. So from the formula for the area of a sector, it's equals to 1/2 r squared theta, where r is the radius of the circle and theta is the angle here, or the central angle. So the angle should be in radians, so we'll first convert 30 degrees to radian by multiplying it by pi over 180. Then we substitute it to the formula 1/2 r squared theta to get the area 58.90 square centimeter. Find the volume of a cone to be constructed from a sector having a diameter of 72 centimeter and a central angle of 150 degrees. So this is the sector that the problem is talking about. It has a central angle of 150 degrees and the diameter is 72, therefore the radius is 36. So this is the 36 cm, so it's the radius of this sector. And then we are going to form a cone from this sector by folding it to obtain this one. So if you're going to examine this side here, this radius now will become the slant height, this one, this L here. And this part here will become the circumference of this base of this cone. So that is equals to 2 pi r. So this arc length here of this sector would become the 2 pi r. So we will use that in analyzing this cone. So for the formula of the volume of the cone, we know that it's equals to 1/3 area of the base times the height. So the area of the base is equals to pi r squared. This is the base of this cone. So that is pi r squared and the perpendicular height, not the slant height. So that's why it's h. So h is the cone's height. And if we're going to examine, we do not have that value yet. So using the Pythagorean theorem from the cone, if you're going to examine the part here, this one, we can actually create a right triangle with respect to the height, the slant height, and the radius. So this is a 90-degree. Then we can get a relationship between the height, the slant height, and the radius. Using the Pythagorean relationship, we can get h as equals to the square root of L squared minus R squared. So we need to get the value of the length and also the radius. From the arc length formula, we know that S is equals to R times theta. So we are looking for, we are referring to the length of the arc. So this arc here. Since this arc now will be equals to this 2 pi r, since equals to the circumference. So we can get the arc length as r times theta, and we know that our r from this given scenario here is equals to 36 cm, and the theta converted to radian is 150 multiplied by pi over 180. So that's equals the arc length would be 30 pi centimeter. So the arc length, the length of this arc is 30 pi centimeter. And since we know that it's equals to 2 pi r, because the circumference now of the base of the cone is equals to that arc length if you're going to fold it. So we can equate C2S or 2 pi r, since circumference is equals to 2 pi r to our computed S, so it's 30 pi cm. So from that we can get the value of the radius as 15 cm. So since we already have the radius, then we can substitute that in our formula here for h. Since we know that the length, the slant height here is just equals to this 36 centimeter also. So substituting, you can get the value of the cone's height. And finally, substitute that for the volume of the cone, which is equals to 1/3 AB times height. Since area of the base is pi r squared, then you just substitute the value of the radius and also of the computed height of the cone. Then finally, we can get the volume of the cone as 7,710.91 cubic centimeter. Sample problem number 10. Each side of a cube is increased by 10%. By what percent is the volume of the cube increased? So the volume of the cube is equals to a cube, right? So if we're going to increase it by 1%, what would be the percent increase also in the volume of the cube if each of the side is increased by 1%? So the percent increase can be written in terms of the formula, the final volume minus the initial divided by initial volume times 100%. So that is always the general formula if you're going to compute for the percent increase. So we have the final value less than the initial value divided by the initial value multiplied by 100%. The final volume of the cone, if we're going to increase it by the area, the side is by 1%. So the side will become, say for example, if it is originally 1, then it would become 1.01. So if we're going to substitute that final volume, which is 1.01, 101% of the original, and substitute for the volume of the cube, which is a cube, and also the initial, which is a cube, then divided it by the initial a cube, and then we can cancel out a cube to get the percent increase. So the percent increase in this case is 3.03%. Sample problem number 11. Compute the surface area of the cone having a slant height of 5 cm and a diameter of 6 cm. So the slant height here is given as 5, and then we also have the diameter is 6, so the radius is equals to 3. So for the formula for the surface area of the cone, that is equals to pi RL. So because we are just referring to the surface, we're referring to the surface area. So the surface area would be pi multiplied by 3 and also by 5. So the surface area is 47.12 square centimeter. Sample problem number 12. A pyramid with a square base has an altitude of 25 centimeter. If the edge of the base is 15 centimeter, calculate the volume of the pyramid. The general formula for the volume of the pyramid is 1/3 area of the base times the height. For this square pyramid, so this is a square pyramid with a square base, the area of the base is the area of the square, which is a squared. That's why we have here a squared. And then since the altitude is the perpendicular height from the apex to the base, and that is 25 centimeter, we can substitute it directly in the formula to obtain the volume of this square pyramid to be 1875 cubic centimeter. So that is how you can use those formula that was presented in the previous slide. You can also do your own research on the other formula and how we can use them in calculating the measurement of solids.